In this video we're going to be looking at the rate equation. Now the rate equation is used to link the rate of our reaction to the concentration of the reactants and takes into account the order of those reactants. So if we consider this reaction here, A plus B forming C and D, the rate equation always has the same general format and you just substitute it in based on what reactants you have and what order those reactants are. So the rate equation is always rate is equal to K, where K is the rate constant, which we're going to talk about in a minute. So rate is equal to K multiplied by the concentration of the reactants. So here we have A and B. And those reactants are raised to the power of their order. So in this example, I'm going to have A as a first order reactant and B as a second order reactant. Now, just looking at the equation, you are not able to determine the order of reactants. So there's nothing you can look at in the stoichiometry of this equation to say, A is first order, B is second order. You have to determine what order they are using the methods that we have outlined in the previous videos. Either the continuous monitoring method, where you look at how concentration varies over time, and then you can use the gradient to work out how rate is changing in relation to concentration, and from that determine if it is zero first or second order. Or you can use the initial rates method, where you repeat the experiment using different concentrations of your reactants and look at the effect that has on the initial rate of the reaction, and then again be able to determine whether it is zero first or second order. So at the moment, we don't know the order of the reactants. There's no evidence here that tells you that A is first or B is second, but I'm just going to assume it is, just so we can talk about the rate equation and the format of the rate equation, and then we'll go through some examples in a minute. So first things first, so rate is the change in concentration of either reactants or products over time. Okay, so the units are always going to be mole per decimeter cubed per second. K here is the rate constant. And we'll talk about that later as to how, what it actually represents, but it links a lot of different things together. It is the function of the likelihood of collisions, the activation energy, the temperature, all of these things that we know affect the rate of reaction. They are all encompassed in the rate constant. Now, no matter what we do to this reaction, the rate constant, as its name suggests, will remain constant for this reaction. So if I change the concentration of A, or the concentration of B, or the concentration of both, well, obviously these two values will change, the rate will change, but the rate constant will not. It will stay the same. And it has no fixed units. Because its units really do depend on how many reactants you have, what order those reactants are, and it will change the units depending on those. And again, we'll talk about how to calculate the units in a minute. So we have rate is equal to K, K being the rate constant, and then we have the concentration of our reactants. And obviously they're going to be in mole per decimeter cubed. And then raised to the power of their orders. So if you've got a rate equation, then you straight away know what order the reactants are just by looking at the power that they're raised to. If you're asked to construct the rate equation, then you need to know the order of the reactants. So they will either tell you, perhaps, or they will give you a graph, a concentration time graph where you can work it out, or they'll give you some initial rates data, again, so that you can work it out and then construct the rate equation. So constructing the rate equation is one thing that you might be asked to do. Another thing could be to determine the value for K. Now, without any data, for what the rate of reaction is, or what the concentration of our reactants are, we can't actually get a figure. But for now, we just settle with the fact that you need to be able to rearrange this equation. So if I want to rearrange this for K, I would rearrange it to K is equal to rate divided by the concentration of the reactants raised to the power of their order. Okay, so we need to be able to make this rearrangement. And from that, we can then work out the units. So to calculate the units, we need to just remember that rate is always mole per decimeter cubed per second. So the top of the fraction is always the same. The bottom of the fraction, however, depends on the reaction. Perhaps you have two reactants in this case that are first order and second order, and you would get a certain set of units for that. But if you had two reactants that were both first order, you would get different units. So we need to look at what are the units for concentration, where it's moles per decimeter cubed, and how many lots of mole per decimeter cubed do we have? Well, we have 1 and 2, but this one's squared, so this one's going to be 2 lots. So in total, 3 lots of concentration on the bottom. So that is going to be mole 3 dm minus 9. So all you have to do is cancel the moles, cancel the decimeters, and then you'll get your overall units. Notice there is nothing to cancel the seconds. So the one thing you can guarantee, I mean, we say that rate constant has no fixed units, but it will always be second to the minus 1, because there's never anything to cancel it. So sometimes if you had, for example, one reactant that was first order, then your rate of reaction, your rate constant units would just be second to the minus 1. Because if on the bottom it's just mole per decimeter cubed, and on the top it's mole per decimeter cubed per second, the moles cancel, the decimeters cubed cancel, leaving you just with second to the minus 1. So no matter what, you're always going to have second to the minus 1 as part of your units for the rate constant. So in this case, we've got a first order and a second order reactant, so we've got 3 lots of mole per decimeter cubed on the bottom. So 1 minus 3 is minus 2. So mole to the minus 2, minus 3 minus minus 9 is positive 6, and then there's nothing to cancel the seconds, second to the minus 1, and there are our units. So we're going to go through some examples, and I'm going to use the same examples that we used in the initial rates video. So we already know from the initial rates method in this reaction that A is first order and B is second order, and we know that because when A doubled, the rate doubled, so it's first order, and when B doubled, the rate quadrupled, so it's second order. So what would the rate equation be? So rate is equal to K. The reactants I have are A and B, so concentration of A, concentration of B, raised to the power of their orders. A is first order, B is second order. So there's the rate equation. It's as simple as that. What is the rate constant? So we need to rearrange this. So K is equal to rate over the concentration of the reactants raised to the power of their order. And then all we have to do is substitute in some values. Now, because we have our table of data, we have some values. Now, like I said, the rate constant does not change as long as we're talking about the same reaction. So it doesn't matter if you use experiment 1 data, or experiment 2 data, or experiment 3 data, you'll get the same value for the rate constant. So just choose one of them to substitute in. So I'm going to use the first one, experiment 1. So the rate is 0.1 over the concentration of A, which is 0.01 to the power 1, times by the concentration of B, which is 0.2 to the power of 2. I'll just type that into my calculator. Give me a value of 250, and that is the rate constant. Finally, what would the units be? Well, on the top we had mole per decimeter cubed per second for rate, and on the bottom we've got 1, 2, 3 lots of concentration, so that's going to be mole 3 dm minus 9, so 1 minus 3 equals minus 2, minus 3 minus minus 9 is plus 6, and then there's nothing to cancel the seconds, so seconds to the minus 1, and there is our value for the units. Let's have a look at another one. So here we've got nitrogen oxide reacting with hydrogen, and when we doubled the nitrogen oxide it quadrupled the rate, so we know it's second order, and when we doubled the hydrogen nothing happened to the rate, so we know it's zero order. So for the rate equation, again, rate is equal to K, concentration of the reactants, raised to the power of their order. Now, you do not need to include the hydrogen because it's zero order. Everything to the power of 0 is 1, so you're essentially writing rate is equal to K NO to the power of 2 times 1. So it's completely not necessary. So when you write the rate equation, you don't include zero order reactants. You would just leave that, and that is your rate equation. You wouldn't be wrong if you did include the zero order reactant, there's just no point to doing it. So I'm going to cross it out. So the rate constant then, so we need to rearrange this for K. K is equal to rate over NO to the 2. Again, you don't need to include the hydrogen because it's zero order, and we'll substitute in some values. It doesn't matter which experiment you use, the rate constant is, as the name suggests, constant, so whether you use experiment 1 data, experiment 2 data, or experiment 3 data, you will get the same answer. So I'm going to use experiment 2 this time. So 1.2 times 10 to the minus 2 over 1.2 squared giving me 8.3 times 10 to the minus 3. Now notice how that rate constant is very different in size or in magnitude to the one we just calculated. There is very little logic to the values for rate constants. You're just going to have trust in the method. Okay, so it's not like when you're doing molar calculations where you know what the ballpark figure should be. Unfortunately, rate constants can be very, very small numbers. They can equally be very, very large numbers. It's very, very difficult to predict whether it's meant to be a large number or a small number. So you're just going to have faith in the method that you've done it right, because the answer you're going to get, it's difficult to see clearly if that is right or wrong. The best thing you can do to check if it's right is to substitute in the values from another experiment. So for example, if I put in the values for the first one, so 3 times 10 to the minus 3 over 0.6 squared, I get the same answer. Now that's, the fact that I got the same value for the rate constant for two different experiments is a pretty good indicator that it's the correct answer. So finally, what are the units? So let's have a look. What did we have on the top? Well, we had rate, so mole per decimeter cubed per second. And on the bottom, we've got two lots of concentration because it's squared. So mole 2 dm minus 6. So when that cancels, you're going to get 1 minus 2 is minus 1. So mole minus 1. Minus 3 minus minus 6 is plus 3. And there's nothing to cancel the seconds. So those are your units. And they are different to the units we had in the last example because there are no fixed units to the rate constant. Right, the third example we did in the initial rates lesson. So here we have PCl3, which when we doubled it, it doubled the rate, so that is first order, and the chlorine, that when we halved it, it quartered the rate, so it's second order. So our rate equation, again, is going to be rate is equal to K PCl3 to the power of 1, because its order is 1, Cl2 to the power of 2. Rearrange it for K. So K is equal to rate over PCl3 to the power of 1. Cl2 to the power of 2. Substitute in the values. So again, whether you use experiments 1, 2 or 3, I'm going to use experiment 3 this time. So 4.8 times 10 to the minus 3 over 0.72 to the power of 1 times by 2.52 to the power of 2. Giving us a value of 1.05 times 10 to the minus 3. And again, if you wanted to clarify if that was the correct answer, just substitute in the values from one of the other experiments. If you get the same answer, then you know that you've got the correct rate constant. So the units for this one, on the top we've got mole per decimeter cubed per second for the rate. On the bottom we've got 1, 2, 3 lots of concentration, so that's going to be mole 3 dm minus 9, and again 1 minus 3 equals minus 2, minus 3 minus minus 9 is plus 6, and there's nothing to cancel the seconds, so there are our units. Finally then, in this example we've got x, which when it doubles the rate, so it's first order, and y, when it doubles, it quadruples the rate, so it's second order. So our rate equation is going to be rate is equal to k x to the 1 y to the 2. Rearrange it for k. K is equal to rate over x to the power 1 y to the power 2. To get the actual value for k, we substitute in, so I'm going to use experiment 4 data for this. So 0.00399 over 0.2 to the 1 and 0.1 squared. Giving us a value of 2, and that is our rate constant. Like I said, the values that come out of these are quite random, so to check that's right, just substitute in the values from any of the other 5 experiments, and if you get the same answer, then you know it's the correct answer. And then for our units, we've got rate on top, mole per decimeter cubed per second, and we've got 1, 2, 3 lots of concentration on the bottom, so mole 3 dm minus 9. 1 minus 3 equals minus 2. Minus 3 minus minus 9 is plus 6, and there's nothing to cancel the seconds. So there are our units once again.